So hello everyone, I'm Norman Wahlberger, and we're here at the University of New South Wales in this course in differential geometry. Last time we talked about curvature and torsion for space curves and the Frenet apparatus, and I ended up talking a little bit about discrete curves, and the battery on my camera went before I finished that lecture. So let me just finish what I was saying about that, and then we'll talk today about geometric and algebraic aspects, additional aspects of space curves. So last time we were talking about discrete version of a curve, which we might represent by this kind of segment, polygonal segment in three-dimensional space, say starting here. And then we can sort of interpret various aspects of the continuous case in this context. So for example, this edge here, this first edge, can sort of be thought of as a tangent vector. So there's sort of the first tangent vector, and then then we change direction, so that's the second tangent vector along the blue line, and then another tangent vector along the red, and another one along the green. All right, so then the curvature of the curve has to do with the connection between adjacent tangents, or tangents which are pretty close. So going from here to here is represented by that angle, the change in angle there along in that plane. That represents the curvature at this point. Okay? So curvature at this point is determined by 3 points. You have 3 points forming a little triangle, and then that angle there is essentially a curvature. So there'll be a curvature there, and there'll be another curvature here, and then there'll be another curvature here, and so on. The torsion, on the other hand, is a slightly higher degree concept and is concerned with the relationship between the plane formed by this, say, first triangle of points and the plane formed by the second triangle of points. So here we start with a plane that's like this. This was actually what we might call the osculating plane, because it's spanned by a tangent and sort of a normal direction. So that would be the oscillating plane at that point, whereas the oscillating plane at this point would be determined by this triangle here. And then the oscillating plane at this point would be determined by this plane here. So every 3 consecutive points corresponds to a triangle, and that's like an oscillating plane. And what we're talking about when we're considering torsion is really studying the relationships between adjacent oscillating planes in a way. Okay? So if we make the transition from this plane to the next plane over, that means we're essentially rotating along that common edge. So we're going from that plane to that plane over there. And the relationship is, of course, also given by an angle. And if you look straight on at the edge in question, you can think about it as being the relationship between, or the angle between that plane there and then the plane that you get by rotating up to the next one. Okay? So it's really the projection, if you look at it right down here, between this plane and this plane, represented by a little angle there. Okay. So, of course, this kind of approach is important in robotics, where we're interested in positions of things. So in order to specify a configuration like this, what the essential aspect is that we have to specify how far we go, and then we have to specify an angle that we're going to go for the next leg. Okay. So once we specify that angle and then the corresponding how far we're going to go, then at the next point we have to specify this by 2 things. We have to say, first of all, what that angle is between this edge and this edge. That's one of the things. But we also need to say how this new plane is oriented with respect to the first one. In other words, how much twisting we have to do to go from the plane that we're on to this plane with the red line. So there's a torsion angle. Whoop, what happened there? There's a torsion angle that has to be specified at every edge. Okay? So to specify the whole configuration, we need to know the relative distances of each segments. We need to know the angles at each one of these vertices. And we need to know the angles between adjacent planes. And that'll be enough to specify the discrete space curve. All right, so let's go back today to a geometric approach to curves, really one of the founders of the subject is Gaspard Monge, who started studying space curves around 1780. And I think it's fair to say, introduced the ideas of curvature and torsion in this three-dimensional setting. So the way Monge thought was this way. So we have some curve in space, and I'm drawing it in a planar way like that, but you really should be thinking about a curve in three-dimensional space like a twisted rope. Okay, so it's twisting and curving in three-dimensional space. That was what he was interested in. Okay, so we can imagine a particle moving along it, and we can talk about a tangent vector. Well, let's say a tangent vector at a point like that, and then naturally associated to such a tangent vector is the perpendicular plane at that point, which is normal to this tangent vector. So we call that the normal plane. Now this is all at some point, so let's call it at P. And then what Monge realized is that if you consider adjacent or almost adjacent points, so for example maybe another point Q here, then of course there's also a tangent vector, and there's also a normal plane. And then he used these adjacent objects to define various things. So for Monge, the osculating plane was spanned by adjacent tangents. So if we take that tangent and find the plane, the common plane that they have together, if the 2 points are close together, then that will be determine a plane. And these two normal planes at P and Q intersect along a line. Let's say here. And as P and Q approach, this line ends up getting close to a fixed value and is some kind of three-dimensional analog of a center of curvature of a planar curve. So he called this line, so the axis at the point P. So that's the meet of adjacent, maybe adjacent in quotes, adjacent normal planes. And you can think of that in a limiting sense, that if we just take the P and Q normal planes, see where they intersect, and then let Q approach P, then that's going to approach some limiting value called the axis. All right, on this axis, this interesting axis, that's associated to the point P. So for every point P, there is a different axis. Okay, so if we choose a different point over here somewhere, P prime, then its axis will be, well, another way of thinking what it turns out to be is if you think of sort of a circle that's approximating the curve near there, then it's really the axis of that circle. It's a line going through the center in a perpendicular direction to the plane of that circle. So as P varies, the axis turns out to sweep out a surface. As P varies, the axis sweeps out a surface which is called a polar developable of the original curve. That's called the original curve gamma. Okay, I'm not going to try to draw it because it's not going to be very accurate, but I hope to show you maybe some computer animations later on in the video. So there's some surface that sort of interpolates, just swept out by all these axes as you vary the point P. Surface naturally associated with the curve. In fact, there's other surfaces associated to the curve. There's also the tangent developable is the surface swept out by the tangent lines as P moves. So you have some curve here, and you imagine at every point I have a tangent line. This is an infinite line. As we move the point around, may not be entirely obvious, but those lines will sweep out a surface. Okay, they will sweep out a surface. It's actually a ruled surface. In fact, it's actually a developable surface. We'll talk about what those are later, but this is an important classification or kind of surface, developable surface. And these tangent developables associated to curves are prime examples of these so-called developable surfaces. So these are prime examples of developable surfaces. Okay, there's also a little bit more that we can say. So if we go back to the point P and we look at this axis here, so here's a point P and here's a line on this normal plane. One thing else that we can do is we can drop a perpendicular from P to this line in this plane. So we can drop a perpendicular and we get a point. All right? And that point is the center of curvature of the curve at the point P. All right. So the drop perpendicular from P to the axis, and we get the center of curvature at P. Let's call it C. Say C. And then the locus of C as P moves gives us another curve, and that's naturally the evolute. We could call that the three-dimensional evolute of the space curve gamma. The locus of C is the evolute of gamma, and in fact it is actually the center of the circle which best approximates the curve around P. Maybe I'll draw it here. So if we draw a circle in this plane that we were talking about, then we get the osculating circle at P. And this direction that we've gone perpendicularly is the normal direction because it's perpendicular to the tangent. So this also gives us the direction for the normal vector. So if we want the normal vector, will also be in this direction, let's say n. So the unit normal n is also in this direction. And then once we have the tangent, t, let's say, the unit tangent, and we have the unit normal, then we can take the third perpendicular vector, the binormal. So 1, 2, 3. Then B defined by t cross n is the binormal. All right, so Monge had the various ingredients of the Frenet formula, but in sort of a different way, not thinking about a unit speed curve, but just thinking geometrically about properties of a space curve. All right, so last time we talked about the Frenet-Serret equations. Let me remind you what they were. So we have some curve, and we're thinking of a unit speed curve. Beta is unit speed curve. And that means that its derivative, b prime of s, which we usually call t, has the property is a unit vector. So its quadrants is 1. Or if you want, take square root, its length is 1. Okay, and at every point we have this frame then again. T n and perpendicular to both of them, B. And then we saw these famous equations that if we take the derivative of t n b, it's represented by this equation, this matrix times t n and b itself. Okay, let me say a little bit about curves and nomenclature here. So when we talk about curves, there's often a little bit of confusion or ambiguity about whether we're talking about the actual geometrical object or the actual trajectory of a point. Okay, so the term curve is sometimes a bit ambiguous. So sometimes it refers to a particular trajectory. For example, if we're talking about beta of s, that's a particular motion, so a particular trajectory, or it refers to the underlying geometric path, which you can just think of as the points which are being traversed, but you don't really care how they're being traversed. In particular, a path actually often has many different parameterizations. So we might usually say a given curve has many parameterizations. And the equations and the related physics really depends often a lot on which trajectory we're taking. So say given parameterization, say a general parameterization, maybe gamma of t. And in this case, the various derivatives, gamma prime of t, gamma double prime of t, etc., can be quite variable. So let's just make a little remark about changing parameterization. Let's suppose, to fix the discussion, suppose we have a little tube and we're thinking about a physical particle that's going through this tube. To make it interesting, suppose it's like a bobsled rider. So somebody who's actually going to traverse this tube. And for the purpose of discussion, let's suppose that the gravity is negligible and friction is also negligible. So that this person's not going to have there's not going to be any external forces from outside or from friction that he's going to be concerned about. So he has an initial velocity shot into here, and of course then he's going to come spewing out the other side. And if there's no loss of kinetic energy, then he's going to have the same speed going in and going out, more or less. But of course, so this is really an example of constant speed. Or uniform, like a unit speed curve. So it's like beta of s. So he could measure arc length by his watch, because he's going at the same speed. Okay, so this person's still going to feel accelerations, of course, because at places where the curve is more curved, the acceleration is going to be bigger, while at places where the curve is not so curved, it's going to be smaller, and maybe here it's going to be relatively small. So here are some, let's say his speed is, let's still call it gamma of t. And so here would be gamma prime of t. Gamma prime of t. Sorry, those are gamma double primes of t, these are accelerations. Gamma prime would be just a tangent vector, which is we're assuming is always the same speed. And of course, if you were actually in a tube moving around like this, you would feel these forces. So you'd feel the tube pushing on you exactly in this fashion, and that would be the thing that's sort of causing you to go. So force equals ma would be very much in operation here. So now suppose we change parameterization. So let's call this gamma prime of t, since it's constant speed, let's assume it's like a unit speed, so that it's actually n, a unit vector. So if we change speed, so let's say inside he has a little rocket and he put the little booster on so that he goes faster inside, or maybe he slows down with some rocket, then his speed could possibly change. So that the new speed is, well, let's call it alpha prime of t, which is new velocity times the old speed. So if we want to differentiate this, then we get that the new acceleration is just by the product rule. It's the derivative of the velocity of the speed times the old tangent vector plus v of t times gamma double prime of t. And what this equation is telling us is that in this case the new acceleration, let's say at this point here he decides to increase the speed. In that case he's going faster He has a little rocket, and that's giving him some extra boost. So he's getting some more acceleration, and that acceleration is going to add to the acceleration that he already has in giving us a new acceleration in that direction. Okay, so to augment the one that we already have, so there's going to be a new acceleration, something like alpha double prime of t. But in particular, the acceleration is still in the plane of the tangent and the normal. Okay. So both the contributions here, one is in the tangent direction and the other one's in the normal direction. So this new acceleration is still in the plane spanned by t and n, i.e. the osculating plane. Okay, it's important to be flexible about our parameterizations because in differential geometry, although it's theoretically nice to have a unit speed curve, theoretically nice, in practice it's often quite difficult to write down specifically, concretely, the equations for a unit speed curve. Reparameterizing can be a major technical challenge. And so although these Frenet formulas are beautiful and elegant, often they need to be augmented by some technology that helps us deal with more general curves when we're not just having a unit speed curve. Okay. So I want to talk about some slightly more general formulas that are quite interesting. So I might write down in a theorem, if we have a general space curve, gamma of t, not necessarily unit speed, then the curvature and torsion at a point of t are given by, so k of t equals gamma prime cross gamma double prime, the size of that, all over gamma prime cubed. Or a little bit more algebraically, let me write down the corresponding formula for the square of the curvature, the quadratic curvature, capital K of t, which is small k of t squared. Well, that's going to be just the quadrants of gamma prime cross gamma double prime divided by quadrants of gamma prime, all cubed. So this here is the square root of the quadrants. The length is the square root of the quadrants. And the formula for the torsion is the torsion tau at a point t is the determinant of gamma prime, gamma double prime, gamma triple prime, all over the quadrants of gamma prime cross gamma double prime. And I'll write that down in an alternate way. So that's alternatively gamma prime cross gamma double prime dot gamma triple prime, all over gamma prime cross gamma double prime dot gamma prime cross gamma double prime. All right, so let's have a think about the proof. I'm going to talk about first the unit speed curve case first. So for a unit speed curve, beta of s, where the parameter is s, in that case beta prime is what we're calling t, and we know that the quadrants of beta prime equals 1. Wow. Equals 1. We also know that the beta double prime, which is the derivative of the tangent, is k times n. That's our first Frenet formula. And so let's have a look at this first formula for the curvature. So if we look at beta prime cross beta double prime, well, beta prime is t, and beta double prime is k times n. So this is going to be just k times t cross n is b. And that's telling us, therefore, that if we take the norm of b cross b double prime and we divide by b prime its length all cubed, well, the length of this thing is the length of this, which will just be k. And the beta prime, we said, is of degree, has length 1. Length of beta prime is 1 because it's a unit speed curve, so the denominator is conveniently 1. So yes, indeed, the formula for the curvature is correct. What about the formula for the torsion? Well, so we know that B, the binormal, is t cross n. And we know from the Frenet formula that B prime is equal to minus tau n. In fact, that's how we define the torsion to begin with. When we differentiate the binormal, it's the coefficient of n that we get, or negative the coefficient of n. And so that means if we want to get at the torsion, we can get at it from this equation by dotting with n. So the torsion is minus b prime dot n, because n is a unit vector, so if you dot it with itself, you get 1. All right, so let's try to evaluate what this thing is and see if we get something that looks like that formula. Okay, so what is b prime? So b prime is, well, what is b itself? B is t cross n. And t is b prime, so we have a b prime. And n is, maybe I should say n is equal to, from this formula, just b double prime divided by k. So there's what b is before we've differentiated, and we need to differentiate all of that. All right, so the b prime is the t, and the n is b double prime divided by the curvature. So we're going to take this formula and we're going to differentiate it. Okay, everything depends on S. All three things depend on S. So we'll use the quotient rule. So the derivative of the top, I'll just write b prime cross b double prime prime for now, times the bottom, minus the top, b prime cross b double prime, times the derivative of the bottom, which is k prime, all over the bottom squared, k squared. And therefore, b prime dot n, which is sort of what we're interested in here, if we dot this with n, what do we get? Oh, I should maybe sort of I have to simplify this first, sorry. Let me simplify that, because I had to differentiate what's inside here. So if we differentiate b prime cross b double prime.
These are betas.
These are betas, yeah. So I have to differentiate what's inside here. So I have to differentiate beta prime cross beta double prime. So the derivative of beta prime is beta double prime. So that's going to be beta double prime cross beta double prime. But that's a vector cross itself, so that will be 0. And the other term will be beta prime cross the derivative of this one, which will be beta triple prime. So we get beta single prime cross beta triple prime times k for that derivative, and the rest is just as it was before. Maybe I'll come up here. All right, so we're interested in tau, which is minus beta prime dot n. So that's going to be minus. What happens when we dot this with n? Okay, well, n is in the same direction as beta double prime. So if I take the dot product of this with n, I'm going to get 0. Because this thing here has a beta prime cross a beta double prime. So this vector is perpendicular to beta double prime. It's perpendicular to both vectors. It's in particular perpendicular to beta double prime. So if I dot it with beta double prime, I'm going to get 0. So I'm only going to get this first component. So I'm going to get minus beta prime cross beta double prime. And I have to dot with n, beta triple prime. This is a triple prime. I have to dot with n, which is beta double prime over k. But there was already a sort of a k on the bottom, so now there's a k squared on the bottom. Okay, but now I can rewrite that because I know what k is from here. K is this thing here. So if I square that and put it in the bottom, I'll rearrange this also. Beta prime cross beta double prime dot beta triple prime. If I interchange these two, then there's a minus sign disappears. And when I replace the k squared with the square of that, I'm going to get the quadrants of beta prime cross beta double prime times over here this beta prime cubed, which is, this is actually equal to 1. It doesn't appear. So we get the formula that we want, beta prime cross beta double prime dot beta triple prime over the quadrants of this, which I can write as beta prime cross beta double prime dot beta prime cross beta double prime. And let me remind you what the significance of the triple product is, so that if we have three vectors, v1, v2, and v3, then when we take this triple product, we're taking the volume of the box formed by those three vectors. So this is the determinant of the matrix that you get by putting the three vectors along the rows. And that's also the same as v1 dot v1 cross v2 dot v3. And it's cyclically invariant, so if you replace indices 1, 2, 3 with 2, 3, 1 or 3, 1, 2, then the thing doesn't change. But if you interchange any two indices, then its sign swaps. All right, so we've established the formulas for a unit speed curve. These are just ways of rewriting the formulas that are valid for a unit speed curve. But why should it hold for general curves? So let's say a little bit about changing parameterizations algebraically. Now, this is a very important topic for physics because in physics we want to create coordinate systems to do computations, but ultimately we want our computations to be independent of the coordinate system that we choose. And that's what's going on here. We've established a result in a particular coordinate system. We need to see what happens if we change that coordinate system. And I'm going to now introduce a kind of algebraic way of thinking about this, again going back to essentially the ideas of Lagrange and contemporaries. All right, so we're going to think about just a general discussion. So if we have a curve, a space curve, say gamma of t, how could we describe that curve? We could describe it in terms of a series in t. Yeah?
Sorry, that theorem you just proved, did you do that in the general case, or did you only prove it in the...
Only in the unit speed case. So I'm making now the transition to the general case now, yeah. So I'm developing some preliminary stuff in order to deal with that going to the general case. All right, so let's express a general curve in a kind of simplistic polynomial way by thinking of it as v1t plus v2t squared plus v3t cubed and so on, where these v's, v1, v2, and v3 are vectors. Right? So we're thinking about the parameterization. It's a space curve after all, so it has to take values in this three-dimensional space. So the coefficients we can think of as being fixed vectors. And I've translated it so that it's going through the origin. Assume gamma of 0 is 0. We can always translate so that we're going to focus on what happens at 0. And we're interested in what kinds of quantities can we define in terms of the vectors which are independent of reparameterization. So it's a natural kind of invariant question. Which quantities involving the vectors v1, v2, v3, and however many we want, are invariant under reparameterization. Well, what kind of reparameterization are we considering? Well, we have some other parameter, say u. So we're going from t to u. And the relationship between t and u might be rather complicated. Let's say that it's expressed in another polynomial relation, that t is equal to, say, a times u plus b u squared plus c u cubed, and so on. So we'll assume that they're lined up so that t of 0 equals u of 0. They both go through, they're adjusted so they have the same value at u. All right, let's have a look at now this original curve re-expressed in terms of the u's instead of the t's and see what happens. Well, maybe I can write a first step here. So gamma of u, well, will be v1 times t. So here is the expression for t. I'm just going to substitute a times u plus bu squared plus cu cubed, and so on. And then plus v2 times the same thing, au plus bu squared, and so on, all squared, plus v3 times au plus bu squared, and so on, all cubed, and so on. But what does that look like as a series in U? So we have to collect the U terms. The linear part in U, there will only be the one part coming from here. So we'll have A times V1 times U. And the quadratic part of the expression will come from here. And also when we square this one here, and there won't be any quadratic parts in U from that one there. So we'll get B times V1 plus A squared times V2. All of that times U squared. And what about cubic terms? We'll get cubic terms from here. And also some cubic terms when we square that. And we'll also get some cubic terms when we cube that one. We could get C times V1, that's a power of, here's a U cubed term. And then for the next one, coefficient of U squared will be 2AB. 2AB times V2. 2AB times V2. Plus A cubed times V3, U cubed. And we could keep going if we wanted to. All right, so what do we have to do? Let's call this something else to be specific. Let's call this, instead of V's, let's call it W1U plus W2U squared plus W3U cubed, and so on. So what is our challenge? Our challenge is to find some invariants, some quantities that we can define in terms of the vectors V1, V2, and V3, or in terms of W1, W2, and W3, so that they're the same. So that given any change of coordinates like this, the result we get when we compute it this way or compute it this way are going to be the same. So we need to write down invariants. Can we find any invariants? Well, you need to stare at it maybe a little bit. The key is to look at just this first quantity. There's nothing invariant. To go from here to here, we're multiplying by A. So clearly things are changing. We couldn't just take the quadrants of this vector, for example, because that changes when we go over here. It's getting multiplied by A. All right, let's go to the second. Let's go to the linear and quadratic terms and compare this thing with this thing. Is there anything that we can write down which does not change when we go from here to here? Well, there is. Okay, the invariant is, let's call it invariant number 1. It's, maybe from this expression here, the quadrants of V1 cross V2. Let's just look at the cross product between V1 and V2. I take this vector and take the cross product. What happens if I take the cross product between W1 and W2? In other words, between this and this. Well, remember that the cross product of a vector with itself is 0. So what we're going to get is just the cross product between V1 and V2, but with an A cubed term in front. So if we take the quadrants of that vector, since we want a number, and we divide it by A cubed, then we'll be all right. What is A cubed? A cubed was the quadrants of V1. So in other words, if you calculate the quadrants of V1 cross V2 over the quadrants of V1 cubed, that's the same as the quadrants of W1 cross W2 over the quadrants of W1 cubed. They're the same. So that particular quantity is invariant under this general change of coordinates. And what's another one? Well, another one is determined by using all three terms. Got here a vector, here a vector, here a vector. Maybe think here. This vector, this vector, this vector. You want a number. If you have three vectors, you want a number. You should take the determinant of the matrix with those three vectors. Okay. So what we're going to do, we're going to take the determinant of the matrix with vectors V1, V2, and V3. And what happens if we do it on this side? What do we get? Well, you have to know that this thing is sort of asymmetric. So if two columns or two rows are the same, then you get 0. So this one with this V1 is going to be 0. When you write down the expression, the only thing that's going to be non-zero is this V1, this V2, and this V3. Together with their coefficients. And there's an a here, an a squared here, and an a cubed here. So we need to divide by something so that this is going to be the same as the determinant of W1, W2, W3. And what we should divide by is quadrants of V1 there's a I said this one here. This one here I said it a little bit wrong, I think. Here I'm going to put a 3, because if I multiply V1 by a, then the quadrants gets multiplied by a squared, and this whole thing gets multiplied by a to the 6th. So up here, what I should have done is put a square root here. Which is telling me that's not really the algebraic thing. The algebraic thing is the square of that. Okay, so it's really, okay, if you allow me to change, it's really this which is the algebraic invariant. Okay, and those are basically the expressions that we're getting for the curvature and the torsion. The torsion is actually this one. So the curvature was essentially I1, or the square of the curvature was I1. And the torsion was this thing divided by I1. Was I2 divided by I1. And this argument shows, some details need to be checked, but shows that these quantities are invariant, and so they don't change when you make this invertible change of coordinates. So the fact that we've proven the result for the unit speed curves means that it applies also for the general curves. So that proves that the formula for our curvature and torsion in terms of determinants and cross products of derivatives. So, all right, so next time we're going to move into surfaces, talk about surfaces.